In this section, we'll look at two more tests for convergence, and the first of which is the direct comparison test, where we're going to compare two sequences. And what we're going to look at is if we have a sequence a sub n that's always less than or equal to b sub n for all values of n in the positive integers, then if b sub n converges, then a sub n also converges. If a sub n diverges, then b sub n diverges. And I'll offer a proof for the first one. What we're going to do is let L equal the sum from n equals 1 to infinity of b sub n. And S sub n is going to equal a sub 1 plus a sub 2. It's the nth partial sum for our A series. And since a sub n is positive and less than or equal to b sub n, then the sequence S1, S2, S3, the sequence of partial sums, is non-decreasing. And bounded above by L. So it must converge. It's non-decreasing and bounded. We have a theorem that says that it has to converge. And because the limit as n goes to infinity of S sub n equals our series, our series must converge. So what we said is that, okay, a sub n is going to be less than or equal to b sub n, and we're saying that b sub n converges to L. So since the a sub n's are always positive, but less than b sub n, our sequence of partial sums is non-decreasing and also has to be bounded above by L. And that means it converges, and since the limit of that series is equal to the series that we're looking at, that series must converge. And then we can do a similar proof for part 2. So we want to know, does this series converge or diverge? And I'm going to call this one my a sub n. We want to compare this now to something that we know about. And what we're going to use for this one is 1 over 3 to the n. And this is a convergent geometric series. The r value is 1/3. One over 2 plus 3 to the n will always be less than 1 over 3 to the n. because the denominator will be slightly bigger for all n in the positive integers, for all terms. So by direct comparison, a sub n converges. And that's all we need to do for this. Here we have another series. We want to know again, does it converge or diverge? We can call this our a sub n. And for this one, we're going to compare to b sub n equals the sum from n equals 1 to infinity of 1 over n to the 1/2. Hopefully you notice a small comparison between this comparison and the one we did in the last problem. We're taking the variable part and basing our conversion on that, comparison on that. And this is a divergent p-series. Now with this one, a sub n is less than or equal to b sub n. And a sub n is always positive. But this tells us nothing. Because if we have this a sub n being less than or equal to b sub n, then in order for the direct comparison test to work, what we're comparing to has to be convergent to say that ours is convergent. So we need to compare this to some other series. Just taking 1 over the square root of n, while it's a good idea, doesn't work in this case. So let's try comparing to 1 over n. This is another divergent p-series. P is equal to 1. For this, a sub n is bigger than or equal to b sub n. And what might help you relate to the theorem that we had, you could rename these. So this is our b sub n, this is our a sub n. So now this converges. Our terms are all bigger than those terms. So by direct comparison, our series must diverge. With these comparison tests, you are using something that you're familiar with, something you know the convergence for, whether it converges or diverges. The next test is another limit test, or another comparison test. It's the limit comparison test. Suppose that all of our terms are greater than 0, and if we take the ratio of a sub n to b sub n, and then take its limit as n goes to infinity, we get a number, where that number is a finite number and positive. Then either both of our series will converge, or both of our series will diverge. And we're going to show that this series diverges. And we're going to compare to 1 over n. This diverges. I'm going to take and use the limit comparison test, and I'm going to be able to look at the limit as n goes to infinity of a sub n divided by b sub n. So my rule that I started with divided by what I'm comparing to. And I can simplify this. I'm taking the limit of n over a times n plus b. This is equal to 1 over a, where since a is a positive number, this limit is a finite value and it's positive. So by limit comparison, the series that I'm looking at diverges. Another example. We'll let this be our a sub n. We want to compare this to something that we're familiar with. And also that's related to this, so that ideally some stuff can cancel out. I'm going to let b sub n be the series represented by the rule 2 to the n over n squared. And what I'm getting that from are these highest degreed variable terms and the power of 2. N over n cubed is 1 over n squared, and then I've got my 2 to the n. So now I'm taking my a sub n over b sub n. And now some nice things kind of happen. I have n cubed over 4n cubed plus 1. This is equal to 1/4, which is a finite positive number. So my series a sub n will do the same thing as b sub n. But the question is, what does b sub n do? And if we look at this rule, as n goes to infinity, the limit does not equal 0. So b sub n diverges. And since b sub n diverges, and when we perform the limit comparison test we get a finite positive number, our series also diverges by the limit comparison test. Here is one more. And what we're going to do is we're going to compare this to the square root of n over n squared, which is the series represented by 1 over n to the 3 halves. And that is a convergent p-series. So now I do my limit comparison test. And since I'm going to be dividing by this fraction, I may as well multiply by the reciprocal right now. N to the 1/2 times n to the 3 halves is n squared, and this limit is equal to 1. Since that's a finite positive number, our series that we called a sub n will converge by limit comparison. Now I want to give you a few more examples to help you determine what we would compare things to. So I'm going to give 3 series here, and then I'm going to look at what we should compare this to. So here are 3 series. And let's look at what we should compare this to. The first one we should compare to the series 1 over n squared. And both of those will converge. For the second one, I should compare it to the series 1 over square root of n. And both of those will diverge. In the third one, I should compare to n squared over n to the 5th, 1 over n to the 3rd. These are both converging. So you really have to look at the terms that you have on the top and the bottom, and kind of simplifying the biggest stuff there will clue you into what you need to do as your comparison. And you want to make sure you're comparing to something that you know whether or not it converges or diverges. So here are the problems that go with this section.